So for this third presentation, I guess there's a couple problem, or one problem here that we'll work out, but this is largely conceptual. This is trying to really tie in together the first two presentations. For example, what we learned on the first two presentations were, one, this issue about a spontaneous reaction. That was the first presentation. By far, that's one of the biggest topics that we need to worry about with this chapter. How do we determine whether something's spontaneous? And the way we did it here was that, well, if this was negative, then it automatically it told us whether it's a spontaneous reaction. Now, at the end of this presentation, I actually want to show you where this formula comes from. Okay, Gibbs free energy formula. And embedded within this formula, we have delta H enthalpy, which is essentially heat for us, and then there's our entropy term. And in the second presentation, we established what was entropy. Now, I've talked about this, a measure of randomness. That's fine for what we're talking about now. How a gas is more random than a solid. A gas has more entropy. Essentially what we're saying is that a gas would have more ways of moving. It can translate X, Y, Z direction in three-dimensional space. It can vibrate. It can rotate. Whereas a solid, it's just sitting there, and there's fewer options in terms of motion for that phase. And then something else we talked about is actually how to calculate entropy. And bottom line is, if you divide the heat by the temperature at which the reaction is occurring, then we can get a measure of this randomness. We can sort of quantitate randomness, if you will. Sort of using the whole concept a little loosely there, but that's essentially what we're saying. How much heat has been transferred into or out of the system with respect to the temperature at which that occurred. That's a measure of entropy. And in that second presentation, we got into a lot more detail in terms of that calculation. We used it in a few places. We will use this thing again in this presentation, but really what I want to do is focus in on the second law of thermodynamics. That's one big topic for this short presentation, I hope. And then the second one is where the Gibbs free energy term, where does that equation come from? Now the second law of thermodynamics, now the technical term is really associated with this entropy notion, but in a more casual way to state the second law, can't get something for nothing, randomness is favored. There's all kinds of definitions for the second law of thermodynamics depending on whether you are whether you're at what point in your education are you? How much knowledge base do you have? That's going to change the second law, the statement for the second law of thermodynamics. It's going to depend on what class you're in. Physics, chemistry, and biology would all have some variation of the second law of thermodynamics. So I'm going to go with Brown and LeMay definition. Any irreversible process results in an overall increase in entropy. Now remember, when we say irreversible process, your typical chemical reaction. And in class, I'm going to talk more about irreversible processes. The video lectures, what I want to get across to you are the essential points of the chapter that you need to, fully function, how to understand the concepts and to be able to do the calculations and sort of tie these together. Honestly, a reversible process is, it's sort of an abstract concept that scientists use to further illustrate, in this case, second law of thermodynamics, which Brown and LeMay does go through, but I'm not going to go through here. I want to focus in on, what does this statement mean? How does it relate it to a particular equation? And this is pulled from the book, and what I'm looking at here, or what we're looking at here, is I guess first off, when we say an overall increase in entropy, we're talking about this term here. What has happened to the total entropy of the universe? And technically speaking, I guess that means literally the universe. Now, on a just in the classroom, in the laboratory, it's sort of narrowed down, thank goodness. The system would be the chemical reaction, or what are we curious about studying, and then the surroundings would be, the immediate surroundings around the system. We don't have to go outside of our laboratory in terms of talking about the surroundings. And so the laboratory itself, I guess you could say, would be the universe. And when a chemical reaction occurs, notice that this says greater than 0. This is actually, that means that the delta S would be a positive value. And that's actually an indication of a spontaneous reaction as well. And I'll come back to that at the end of the talk. But that's essentially, the text statement of the second law, and then if you want to express it as a mathematical concept, that's what it looks like. And one way to think about this, there's a couple of consequences here for the second law of thermodynamics. Some heat will always be wasted during a chemical reaction, and then that heat is used to drive the entropy up in the universe. And it can, the increase in entropy is going to happen somewhere, either with the system or with the surroundings, when anything occurs on this planet. Now what I want to do is, take this equation and illustrate it with a particular problem. Illustrate it with a physical example, so we can sort of get a better feel for numerically what all this would look like. And the one that I'm going to use, same one as Brown and LeMay. Again, we pay enough for this textbook, we might as well use the thing. And the description that I'm providing you is a different description than what the book is going to provide for you. So when you read through the book, and I sort of intend on these the text and the video to be related to one another. And I guess I should mention this is section 19.2 is where I'm at right now. When I talk about Gibbs free energy, that would be section 19.5. I'll remind you when we get there. And it's a simple process. This is just ice melting. And one thing, notice that what I've tagged here is what happens to the system and what happens to the surroundings as ice melts. So we have this would be the system. If ice is melting, if it's going from a solid to a liquid, well, there must be, you have to add heat to this reaction to get the thing to melt. So there we have the system is gaining heat. Well, where is that heat coming from? Well, we can sort of illustrate it like this. That's our system. That's our surrounding. Well, if the heat is going to come in to the system, it's being pulled from the surrounding. So essentially what happens, there's a plus Q associated with the system, and it's gaining heat, and then the surrounding is going to lose Q, and it's going to be a negative value for that process. And really, Q in both cases are going to have the same quantitative value for this particular example, and that value would actually be the enthalpy of fusion for this process. What is the heat change associated for this particular phase change, and it can be looked up in tables, and it would be 6.01 times 10 to the third joules, and this would be per mole. Now sometimes it's written as joules per mole, and I'm just going to use the joule, the unit, for this example that I'm going to go through. Assume that this system that we see down here this guy here is 1 mole of water. You know, well, that'd be 18 milliliters, or equivalent of that in a solid form, as it's melting. And so the amount of heat that that ice cube would absorb is equivalent to this delta H of fusion, and that is the Q that I'm going to use for the calculations here. Now, for this process to occur, I just want to point something out to you. I've run out of room here, but that's not unusual for me. You know, if the ice cube is sitting there as a solid, that means it's at 273 Kelvin, 0 degrees Celsius. Let's make the room at 310 Kelvin, and there's a heat change or a temperature change between the surrounding and the system, and that's typically what you see for these systems. And I don't want to get too far into it, but like when you look at some of the nitty-gritty details of entropy and the development of this on a more advanced level, oftentimes you see a high temperature and a low temperature, and that heat transfers between those 2 points. And during that transfer, then the system can do some kind of work. You see these diagrams over and over again in physical chemistry textbooks, and so this idea of a high temperature and a low temperature is something that's in some ways very common when you start talking about this particular subject. So I wanted to pull that in with this example. So, you know, as a picture, this is probably sort of what it looks like, and as an equation, we use the same concepts here. And again, here's our first equation from the second law. And to make this, you know, that second law equation, you say this is greater than 0 for a spontaneous process. Now, I'm just going to look at I'm going to calculate the amount of entropy for the universe, for the entire, for the system and the surroundings for this particular process. And I've just sort of laid out the derivation of the expressions that you're going to see in the textbook, and we still have, there's our reaction, there's, you know, the immediate surroundings of the reaction. Remember we talked about the entropy change equal to heat transfer with a particular temperature, and notice that I've used my subscripts here, surroundings here, systems, the chemical reaction here. Well, as it turns out, remember, well, we go back to that last slide, that the Q of the surrounding and the Q of the system had equivalent, at least the actual numerical value was the same. The only difference is that you would have a change in sign, and that's going to show up in the next part of the next slide. So just hold on for that. But what we're trying to do is we're setting up an expression now. You know, we know that the 2 different temperatures at which this is occurring, the enthalpy change for the system and the surrounding, they are known. Remember, that would be this value here. You would just, you know, the Q and the Q that have that same magnitude change is just a different direction, plus and minus. And that is what's included in this expression here. And I've written all over it, haven't I? Try to get there to that. There we go. So there's the conclusion, at least for the equation setup, if you will. You know, now we can actually calculate the change in the universe for an ice cube melting at those 2 different temperatures. Remember, this better be equal to 0. Well, I guess we know it's going to be equal to 0 because we know that if we set an ice cube out in the middle of a warm room, it's going to melt. It's a spontaneous process. You know, once you start that thing going in that particular environment, it's just it will go to completion, and that's for that particular example. You know, the reaction proceeds forward without any kind of extra intervention there. And now if we want to, there we go. Let me plug some numbers into this thing so we can see the numerical value for delta S of the universe. since I know we're so curious about it. Remember this, the enthalpy change for the system, well, it gained heat. The ice cube is melting, has to gain heat to do that. That value is simply what I gave you earlier. It was setting at 273 Kelvin, and then, you know, this minus sign, I'm going to factor it in there, minus sign, you know, for whatever heat that the system gains, the change in the surroundings is equal and opposite. If you look back at the derivation, you see that this was the negative delta H system was equal to the delta H of the surroundings, and the surroundings are at a little higher temperature, 310 degrees, or I'm sorry, 310 Kelvin. Joules Kelvin minus 19.4 joules Kelvin, and you can see already this is a positive value, 2.6 joules Kelvin. So during that process, there is an increase in the entropy of the universe. Now, the place where the entropy is we're going from a solid to liquid, and so it's actually the system that's, well, we see here, the system is gaining more entropy than the surroundings losing a little bit of randomness due to the heat transfer. Okay, so that's one way that one can view when you have a spontaneous reaction. Again, positive delta S of the universe, and that's what a calculation would look like there. Now for us, it's the Gibbs free energy that we're worried about, right? That presentation number 1, I started out with Gibbs free energy, and I guess I could, let me remind you what it looks like here. There's an enthalpy component, heat component, and an entropy component. I want to derive the Gibbs free energy in much the same way that the book does. I'm just here, I have the opportunity to sort of, you know, write on the PowerPoint and sort of talk our way through it. And again, I'm beginning, essentially, this is partly from the second law of thermodynamics. Again, if you look in the book, the second law of thermodynamics puts some a finer edge on it. You know, this expression is positive for a spontaneous, irreversible reaction. Okay, but this is where my starting point is. You know, the problem with using this equation to determine spontaneity of a reaction, we got universe in here, we got the system, and we have the surrounding. So there's a lot of components that you have to keep track of as you go through a calculation. Like you can go through a calculation like I did here to determine whether it's a spontaneous process or not. Now, Gibbs free energy, what it's doing is it's taking this expression here and it's trying to switch everything over to the system. So all the measurements are respect to the system after this derivation is through. And let's just walk through the stages and see what we're up against. You know, because if I'm looking at this expression, well, this is okay. I mean, that's already talking about the system. Remember, the system's a chemical reaction. That's what we're curious about. That's what we can control. That's what we can follow. We're not necessarily going to be able to follow the surroundings all that well. But the entropy change for the surroundings, something we've established, is just the negative of the heat flow in or out of the system divided by T. And that, remember, for a reaction, a chemical reaction occurring at constant pressure, this is chapter 5. First Gen Chem is really where this came into play. That relationship. We talk about heat transfer. If we want to talk about a thermodynamic parameter, then that's an enthalpy change of the system. Now we have an equation where we can plug this in now into this portion of the expression, and we're going to get this guy. And I'm going to do a little bit of rearranging. If I multiply through both sides by, and I see a typo there. That should be a negative instead of that positive. if I multiply through by negative t on both sides of this expression, what I'm going to do is I'm going to get rid of that t. Yeah, I've simplified the expression, and notice that now I've switched one side of the expression just to, parameters dealing with the system. And then we have this new term that we see, temperature, negative temperature times the change in the universe. Well, what we do here now is there's our expression before again. Well, actually, notice what I did. It's still system and system on the product side. I've just let me go back to this. All I've done is flip these two expressions. Nothing fancy. Okay, no complicated algebra there. What I'm trying to do is trying to get it back into that arrangement. It's why I went through that little step. And what we do now is this component. Remember, it was delta S of the universe. If it's greater than 0, then we have a spontaneous reaction. This is coming from the third law of thermodynamics, or second law of thermodynamics. Well, we redefine that as the Gibbs free change for the system. And that's all we're doing there. So this delta G, what's wrapped up into that one parameter that we can calculate based on numerical values or experimental data for the system. This delta G has wrapped up in it the temperature term, and then most importantly this change in the universe, or the entropy change for the universe. It then allows us to calculate. One thing, it cleans this up a bit, and again it allows us to figure out whether the particular reaction is a spontaneous reaction or not. And so now the conclusion here. Now this middle table we've already seen. If it's a negative delta G, then I said it was a spontaneous reaction from the first presentation. And when I talked about that, I specifically talked about heat and then the entropy change, what's happening there. But now I'm trying to wrap that up and tie it in to this notion of the second law of thermodynamics, which is really an important concept to link between the two. I could have just left delta G as is and just say we'll use that and not worry about anything else. But I want to tie it into the second law of thermodynamics, because this is, in my opinion, one of the more important laws that has been developed by, or has been observed by humans in the past 200-300 years. And you can see that, let's just take one other example. If it's negative, that means that this would be negative. Negative times a negative. Well, what does that do? That makes delta G a positive. And we know that for positive delta G, then it's a non-spontaneous reaction. So when I say non-spontaneous, that means that at the conditions described, it's not going to go forward. A spontaneous reaction means at the conditions described, eventually the reaction will occur. Which is actually an important point. It may take a very long time for that to happen, but we know that eventually it will reach the set of products that we have there. So if we're saying that this is a spontaneous reaction, thermodynamics says yes, it will occur at some point. We'd have to use kinetics to say, tells us how quickly it occurs. So just because something is spontaneous does not mean that it's going to take place right in front of your eyes. A good example, I think, a piece of paper. Eventually it will decompose. That is a favorable reaction, but it just may take a few thousand years. So the kinetics is telling us what time frame we're dealing with, and all thermodynamics is telling us is yes or no, essentially. Okay? And then the last thing, once the reaction stops changing, you would find that delta G comes in at 0. and we'll see some of these in the calculations. That all that's saying is that we're at equilibrium. The process. If we have a dynamic system going from A to B, and then give it 5 days or something, and it reaches equilibrium. This is what we're talking about. Yes, the delta G change, if you calculate it, would be 0. And I guess technically you'd say that delta S of the universe would be 0 at this point. But in the process, during the 5 days, there would have to be some kind of, if this, the way I'm describing here is a spontaneous reaction, over those 5 days, there had to be some increase in the entropy of the universe. So I guess that's one reason why I put the quotation marks around 0. So usually I reserve the 0 label for the delta G there. Okay, and you notice this is of all the presentations, this is a pretty short one. It's just a conceptual game that we're playing. Oh, and I'm sorry, this Gibbs free energy talk was section 19.5. All I wanted to do was just sort of tie those two comments together. I'll probably talk more about them in class, but I wanted a short presentation where you can listen to it 2 or 3 times, because the conceptual hoops that you have to jump through for these two topics can be rather challenging, I believe, especially when you first hear them. So I'm hoping that this will help you out a bit. Okay, thanks.